Welcome to Cloud on Air, live webinars from Google Cloud. We're hosting webinars every Tuesday. My name is Sheeta, and today I will be talking about AI inference with GCP on Intel. You can ask questions anytime, and we have folks from Intel and Googlers who will be taking your questions. Let's get started. We will be talking about value proposition of Intel Xeon in GCP and how to configure your GCP environment with Intel hardware and software optimizations, and tools to get the best performance for your AI application. We will present to you some of the work that we have been doing with Google over the course of 2 years and how we can bring these optimizations and tools available and easy to use in GCP. So here's an agenda of the talk. First, we will go over a brief overview of Intel and AI, our strategy and strengths. We will continue with talking about our Xeon CPUs available in GCP. Then we talk about how we get the best performance for AI applications from tuning and optimizing different frameworks to run best on our hardware. And lastly, we talk about our 2+ years of collaboration with Google Cloud to make this performance easily available to GCP developers. I'd like to start with a real example of an AI customer to highlight the value that Intel brings to AI. This is showing the life cycle of an industrial defect detection project. And we are showing the breakdown of this life cycle into different phases. While other projects will be different in time breakdown, the steps are typically the same. At the bottom, overall time to solution is the complete AI journey, including steps from opportunity assessment to development and deployment, and ultimately evaluation of the end result. In the middle, we zoom in on the develop and deploy portion of the overall solution, which includes sourcing data, proof of concept development, inference deployment, as well as integration into a broader application. At the top, we zoom in further on the proof of concept development itself, where you can see that data preparation took a majority of the development time, followed by training the model and testing plus documentation. As you can see, there's a lot that needs to happen before and after the compute-intensive part of the life cycle, which we refer to as the core machine learning and deep learning phase. Intel works with customers across the entire AI life cycle to speed up overall time to solution. It's important to think about the overall flow of your data, including the data management and other headaches, and what would get you to the deployment faster rather than accelerating one portion of your solution at a premium. Now, in order to expand on this concept a little more, let's take a quick look at the multiple approaches to get your data ready before your deployment and development cycles. A key factor in deciding your approach is where you land on the data spectrum. Is your data coming from one source or many? Is it structured or unstructured? How much volume are you dealing with? Is it mission critical or not? Is it streaming live or batch? Who needs access to it? These are some of the questions that you should be asking before you start your process of the deep learning journey. Are there any regulatory requirements? Depending on your answers to these questions, we would recommend different approaches and different tools to integrate, store, process, manage, and analyze your data. For example, if you're dealing with live streaming data that's coming from multiple sensors, you would want to consider tools for unified, high throughput, and low latency real-time data ingestion. The bottom line is there are many different approaches to set up your data and get your data ready for your AI development and deployment. And Intel works with a vast ecosystem in this area to optimize their solution to run best on our latest hardware. Leveraging these optimizations will provide the best performance for the data prep cycle, as well as little to no overhead and headache for managing and moving your data. Now that we talked about different cycles before we get to the core machine learning, deep learning of your AI application, let's take a quick look at Intel's complete portfolio of software and solution stacks that run on Intel's diverse portfolio of hardware products. With our software stack, we target every level of AI expertise and engagement, from library developers to data scientists to app developers. We also have a rich catalog of solutions based on internal and public use cases to share with solution architects across different segments. To simplify the things a bit, I'd like to focus on a handful of these tools today that most apply to GCP developers. Let's start with Intel Xeon processor, which is the foundation of our AI solutions, especially in GCP. We will be talking about some of the improvements in the latest generation of Xeon CPU and how that would translate to better performance for your AI application. Next is MKLDNN, our open source deep neural network functions for our CPU. Library developers can use these primitives to accelerate performance on our hardware. Then we focus on the next layer of stack with Intel optimized frameworks, especially TensorFlow for the purpose of this presentation, as well as Intel distribution of Python. And lastly, we will focus on our deep learning development toolkit, OpenVene, which makes it possible to run inference with optimized performance on a wide variety of hardware backends using a unified API. Intel has been partnering with Google for many years on their data center infrastructure, and since 2016, we have been collaborating closely with GCP on cloud solutions that run on our hardware. To summarize the strategy for our engagements on AI, there are 3 pillars that we focus on. First is the product. Through our very close collaboration with Google, GCP was the first cloud service provider to provide access to our latest generation Xeon Scalable processor in their cloud environment, even months before general market availability of our product. Google is always at the leading edge of the technology, and we continue to collaborate to provide time to market for our products for GCP developers. The second pillar of our strategy is working on tools and libraries to enable maximum performance from our hardware. This work, as I explained earlier, spans across multiple layers of software, from primitives and libraries to unified compilers and SDKs, and optimized deep learning and machine learning frameworks. And lastly, we collaborate with GCP to make these tools available and ready to access, easy to access in the GCP environment for the developers. So let's talk a little bit about our product. Intel Xeon Scalable product, also known as Skylake, is the latest generation of Intel CPUs available in GCP since first quarter of 2017. These processors increase the number of CPU cores from previous generation, which translates to 50% larger VMs. You can now select Skylake-based VMs with up to 96 vCPUs and memory as large as 1.4 terabyte. Skylake also incorporates many microarchitectural advancements, including significantly larger caches, which translates to applications being able to store larger data structures closer to the core. If your data structure doesn't fit on the core, you have more memory bandwidth to access the memory faster. And on the execution side, Skylake decreases the instruction latencies of many instructions and adds wider execution. At the same time, Skylake implements the latest generation of Intel vector instructions, AVX 512, which provides twice as wide as previous generation vector sizes and can boost floating point performance up to 82%. All of this translates to faster vCPUs and containers based on Skylake in GCE and GKE, as well as other GCP products. As you know, one of the essentials behind convolutional neural network modeling is matrix multiplication. In Xeon CPUs, we're accelerating instructions to perform these operations as efficiently as possible. Skylake today supports FP32 vector multiply and add instructions, as well as int8 instructions. Next generation of Intel Xeon processors offers our new VNNI instructions. VNNI stands for Vector Neural Network Instructions and includes hardware acceleration for int8 convolution instructions. In next generation of Intel Xeon processors, three AVX instructions to perform int8 operations are fused into one, providing speed up due to consuming less clock cycles. We're working very closely with framework developers to make these instructions integrated into their frameworks so that they can take advantage of the performance boost that these instructions bring to your application. So we talked about our new instructions and all the goodness in the hardware that our new products bring to GCP. However, any hardware is only as good as the software that runs on top of it. So in addition to providing the features in our hardware, we have been heavily focused on software optimizations to leverage all the features in our hardware. We have been engaged very closely over the last few years with different framework developers to integrate our libraries and upstream our optimizations. Here's an example of our optimization work over the course of 1.5 years. From July 2017, which is when we launched Skylake CPUs publicly, there has been about 5.4x improvement in inference performance solely from software optimizations. This is a comparison on the same Intel hardware and can speak to the power of our optimizations. From now till next year, when our next generation Xeon CPUs will be available publicly, we're expecting inference performance to roughly double due to the new hardware acceleration instructions implementation and the additional performance optimizations. This chart is based on ResNet 50 performance. Obviously, for a less compute-bound workload where there are other bottlenecks in the hardware, the results will be less pronounced, but still very significant. Now, let's focus on TensorFlow for a bit and talk briefly about the framework optimizations. We spoke earlier about our optimized deep neural network libraries. MKLDNN, as I mentioned, is our open source math kernel library for deep neural networks and the main building block of our framework optimizations. MKLDNN is highly optimized using sometimes very low level, as low as assembly code, and the API has been developed with feedback and integration and interactions with major framework owners. The optimizations are done at multiple layers. First, all the primitives such as convolution, matrix multiplication, and batch normalization are rewritten to take advantage of the latest wide vector instructions. Next, the different layers are parallelized to allow for efficient use of all the available cores in the hardware. And lastly, balanced use of prefetching, cache blocking techniques, and data formats that promote spatial and temporal locality are used to make data more available when the execution units need it. In addition to using MKLDNN primitives, we use other techniques to integrate into TensorFlow. There are things that we do like layout optimization, replacing default TensorFlow operations, fuse operations, propagating intermediate states, and we have our custom CPU pool allocator, which basically helps with avoiding costly page misses and page clears. We have been working with Google on these optimizations for 2+ years and continue to collaborate to realize the gains from the new instructions and framework performance. Now, in addition to TensorFlow and other deep learning frameworks, we have been contributing our optimized libraries to Python. We have accelerated NumPy, SciPy, and scikit-learn with with Intel MKL. Our optimizations are available through Conda and Anaconda Cloud for general public use and are upstreamed back to main Python trunk. If you're interested to find out more on Intel distribution of Python and some performance proof points, we have a good write-up on this on our Intel website, software website. I think there's a link on this slide that you can refer to. And here is just an example of using the scikit-learn library in GCP environment to achieve significant performance speed up. This is using a k-means clustering algorithm. You can see gains of up to 23x faster for using the Intel scikit-learn versus a stock scikit-learn library from Python. And this is run on GCP on a 96 vCPU Skylake instance. Now that we talked about some of the Intel optimized libraries and frameworks, I'd like to spend some time to tell you a little bit about our collaboration with Google Cloud to bring the performance of these optimizations to you as an easily accessible asset in GCP. We have created Docker images with both Intel optimized TensorFlow and Intel distribution of Python on Docker Hub and GitHub. There's a link for these to access these Dockers. Basically, these will bring all the goodness of our software as a one-click Docker download for your image, so you can use these to develop faster and more efficiently. We've also been working with Google to make Intel distribution of Python as well as some Intel performance libraries available on Google Container Registry. The Intel performance libraries include libraries like Intel Mac Kernel Library, Intel Threading Building Blocks, Intel MPI, IPP, and Data Analytics Acceleration Library. For you to be able to use these libraries on your VMs, you need to make sure that your runtime is actually available for these libraries, and there's good instructions on the link on the website where you can download these, basically download the runtimes and make them available in your VM instances. In addition to containers with Intel optimized libraries, we have been collaborating with Google to create optimized virtual machine images. In addition to ease of use and deployment, these images guarantee that the developers are always leveraging the latest version of the optimizations through these images. Recently, GCP released 2 Intel optimized VM images, one with TensorFlow 1.12.0 using the latest MKLDNN and MKL libraries, and another one with Intel optimizations for 3 Python libraries, NumPy, SciPy, and scikit-learn. These images automate setting up the environment variables with the right variables and are available through Google Cloud Marketplace, GCE OS images, and command line interface. I would like to spend a little bit of time to walk you through how to get started with selecting the right platform in GCP and accessing the optimized images. To start off in Google Compute Engine, when you're creating an instance, go to the CPU platform pull-down menu and select Intel Skylake or later to guarantee that your application will leverage the latest hardware enhancements. We talked earlier about the advantages of Skylake over previous generation CPU. And I'm glad to mention that in terms of availability, Skylake is now available in 16 out of 17 GCP regions. If you're not using the console, you can use the min CPU platform flag in G-Cloud shell to select your CPU. And any of the 16 zones with Skylake availability, you can set the flag to Intel Skylake when you create your VM to guarantee running on Skylake. As we discussed earlier, the main premise of the VM images is to make Intel optimizations and tools easily available to GCP developers. One of the ways for accessing the VM images with Intel optimized TensorFlow or Intel optimized Python is to use Google Cloud Marketplace. In your Google Cloud Console environment, click on Marketplace and look for deep learning VM images. With one click, you will be able to deploy these images on your VM. You can also access these images on GCE. If you're looking for more control when you're setting up your VM, deploy these optimized OS images by changing the boot disk and selecting one of the Intel optimized images. To take full advantage of the optimizations on the latest architecture, make sure that you select your CPU platform as Intel Skylake or later while doing this. And if you're using Google Cloud Command Line interface, you can launch the VM images using the following command line options. Set the image family variable to one of the Intel-specific image types at the time you are creating your instance. You can also set the min CPU platform variable to the latest Intel CPU Skylake. Now, I'd like to talk to you about our toolkit. So we talked about the libraries, we talked about different layers of software stack, and we focused on the libraries and frameworks so far. And I'd like to talk to you a little bit about our toolkit and what helps you develop for Intel hardware. So our latest project with Google Cloud has been on Kubeflow pipeline, and we've been working on integrating part of our development toolkit into the Kubeflow pipeline. Earlier, we talked a little bit about our software toolkit with a common API across different Intel hardware. This software toolkit is known as OpenVene, which stands for Open Visual Inference and Neural Net Optimization. OpenVene has 3 main components. First is the Deep Learning Deployment Kit, or DLDT. The second one is an OpenCV and Media SDK used for traditional vision and video processing. And third is a collection of pre-trained models and tutorials. In summary, OpenVene provides a unified programming model across hardware, is optimized for performance and memory footprint, is extensible for custom workloads, provides broad operating system support, is self-contained for a simple out-of-the-box experience, and is open source for the community to contribute and enhance. The components that we will focus on today are basically the DLDT, which offers a model optimizer and an inference engine with unified APIs across different Intel hardware. So Intel and Google are partnering to bring the performance and ease of use of DLDT to GCP developers by adding DLDT containers to the Kubeflow pipeline. Suppose you're a data scientist creating an end-to-end solution based on some medical images. Your work can be done through multiple different containers. The data ingestion, data transformation, and data validation containers facilitate reading the data, transforming the data to the expected format, and validating the data as usable and properly labeled. This data is passed to the trainer container. The output is a trained model that is passed to the model validation container to ensure the model is ready for deployment or serving. The trained model is then used for serving by your end party. The way OpenVene is integrated into this flow is that the trained model is fed to the DLDT model optimizer. The model optimizer generates optimized IR, and then the optimized IR is fed into the serving with DLDT container, basically using the inference engine to run this as efficiently as possible on the Intel hardware backend. So here we have some examples of integrating Kubeflow pipelines with OpenVene containers. In the links provided here, we have the 2 examples, and we invite you to go ahead and try these examples and just go through the flow of integrating these containers into the Kubeflow pipeline. You can learn more about OpenVene and its benefits using the link at the bottom. Also, my colleagues are going to deliver a webinar on Introduction to AI Pipelines and Intel OpenVene integration that I highly encourage you to watch to learn more. So just to wrap up, here are some resources for more information on Intel resources for AI developers. Intel AI Academy is the best place to start to learn more about Intel's assets and tools. AI Builder Solution Library is a great one-stop shop to find Intel AI technology-based solutions for different verticals. And Intel's landing page on GCP is a great starting point to learn more about Intel technologies enabled in GCP. With that, I would like to thank you again for the opportunity of introducing some of our AI technologies in GCP. Please stay tuned for our live Q&A. My colleague Banu will join to help answer some questions. We will be back in less than a minute. So I have Banu here with me, and we're going to try to answer as many questions from the audience as we can. We've collected some questions while I was talking, and Banu, so here's a question asking, what are some of the examples of customers using Xeon for AI?
That's a really good question. So for AI, we have a lot of customers who use our Xeon processors for both machine learning and deep learning workloads. Specifically in deep learning for AI, we have two different types of workloads for inference and for training that we support. Our customers use Xeon Scalable processors, our Skylake CPUs, for streaming inference and batch inference. One example for streaming inference that we recently talked about was Taboola. It is a recommendation engine that does web serving for web serving applications. And they use our Xeon CPUs for bringing the data in, to stream it in, and then do real-time inference on the data. And they offer around like 360 billion recommendations for billion unique users every month. So that is one example of streaming inference. And then for batch inference, we have customers like GE Healthcare that uses Xeon CPUs specifically for image recognition workloads, and their workload is on drug, like more like CT scan and pharmaceutical related. And they use the Xeon CPUs for batch inference, which is when they have a database and collected set of data, and they use that to run inference in large batch sizes. And they have realized, tremendous amount of performance improvements by going to the Xeon CPUs. And then we also have training workloads. We have companies like Novartis in the pharmaceutical industry doing high content screening, which is basically looking at really large image sizes. If you look at some of the benchmarks that we use, for example, like ResNet 50, they use an ImageNet database, and that is a smaller set of images. But in real life, our customers use much larger image sizes, and Novartis is one of the examples on training, where they have achieved improvements in the time to train and throughput using the Xeon CPUs. So those are some of the examples of our customers using the Xeon for AI.
Right. I think the next question kind of alludes to that as well. The next question is, can we also run training on Xeon? So we've been talking about inference and how to set it up and how to use it on Xeon and GCP. Do we have any examples of customers running training on Xeon? Is it doable?
Right, yeah, that's a good question. So Xeon CPUs are multi-purpose CPUs which are used for a wide variety of workloads, and deep learning is a subset of one of those workloads that is very important to Intel and our customers. As part of that, you can run training on the Xeon CPUs. One of the examples I alluded to was Novartis. But there are a few others that I can touch upon. For example, in the convergence of HPC and AI, we have workloads that run for our customers on tremendously large databases. One of the examples is recently we talked about in the Supercomputing 2018 conference on how Gen Z, a French research institute, used Xeon CPUs to scale training across multiple CPUs, almost 128 nodes, achieving a higher level of scaling efficiency and getting to the accuracy that is needed. So that is one of the examples of how you can run training on Xeons. Do you want to add?
Yeah, actually, as a matter of fact, in GCP, we've had a few customers that are doing training on Xeon. Their applications go across from visual effects to satellite imagery. Descartes Lab is one of them who has publicly, announced that they're doing training on Xeon, and there are a couple others that are actually doing this in GCP environment.
Okay. Yeah, one other example that came to my mind was also like CERN, that they use the Large Hadron Collider to, and they have a massive amount of data set that they collect, and they run like high performance computing, like Monte Carlo simulations to do that. And they use Xeon CPUs to do distributed training across those 256 nodes. And we showed in one example on 3D GAN, which is generative adversarial networks, and that showing scaling efficiency across multiple Xeon nodes as well.
Got it. Okay. Great. So let's see.
I can ask you the next one. So when can we get access to deep learning boost on our VNNI on GCP?
Okay, so that's a good one. So deep learning, boost, and VNNI instructions are available in our next generation Intel Xeon CPUs. We're actually shipping samples to our customers towards the end of this year. When it's going to be available in GCP is really a question for GCP reps. So I really encourage you to be in touch with your GCP reps in order to find out their timelines on when they're going to make this available in their platform. So I have one for you now. Okay. Actually, let's go to the last one first because I want you to answer that one. And then if you have time, we'll come back to the previous one. So what different topologies and frameworks are optimized for Intel hardware?
That's a good one. So you did touch upon like the Intel portfolio slide and showed like the different frameworks that we optimize for. So to summarize, we do like TensorFlow primarily for framework optimizations. But in addition to that, we also do like MXNet, Caffe 2, and then PyTorch and Paddle as some of the examples of the frameworks that we optimize for. In terms of topologies, we do a wide variety of topologies, and they're very related to the use cases that our customers are applying for. For example, we run image recognition, which was like the ResNet 50, Inception v3 examples. We do object detection, which is like YOLO is an example of that. We do image segmentation, where we are looking at specific segments of an image, and that's like mask R CNN. We also do like language translation, which is the neural machine translation workloads. And then some of the other ones that come to mind are like text-to-speech. WaveNet is a good example of text-to-speech workload, and even recommender systems, for example, like wide and deep or neural collaborative filtering. So it's basically a huge range of topologies that we optimize for on these different frameworks.
Okay. So not only libraries and primitives, we also do frameworks, and I think that's the part that we also work with different topologies and different workloads.
Right.
And I think probably we have time for one more question. What is the benefit of Intel optimized software, and why do I need it?
That's a good question. I can start and then you can add to it.
Sure.
So what Shide has been talking about to you today has been about why, like what are the different things we can do, but why do we need to do it, right? For example, the hardware that we build, like Skylake, has an AVX512 instructions, and our next generation Xeon CPU will have like the VNNI instructions. In order to get the performance out of these instructions, you need the libraries that are developed on top of it to use these instructions. And then once you have those libraries developed, you need like the framework to call these libraries. So that is why we say that you need the latest optimized software on Intel hardware in order to get the best performance. Do you want to give like a GCP?
It's pretty much the same thing in GCP. I mean, as long as you have the frameworks, the topologies available, make sure that you're using them. Make sure you're using the latest and greatest of the hardware and the software. Give it a try, and your performance is going to see the advantage and the boost.
Right.
So I think with that, we're going to close. Stay tuned for the next session, introducing AI Hub, the one-stop catalog for everything AI. Thank you.
Thank you.